I'm sorry I didn't give you a break today, but we'll just finish a little bit early then. Anyways, you had like a 2-hour lunch or something? Oh, still long enough. Okay. This lesson is quite straightforward. Centre of gravity. No singing in physics. Yes. Oh goodness, am I in the wrong room? I thought I was here for the next 4 hours. I know, I could be. The students will tell you I could be wrong. You think you're in here?
Yeah.
Oops. What room are you normally in at 2 o'clock? Is it this room, or do we have to move? No. You normally have physics. Can you just check your timetable there?
Okay, we'll go into 302 then.
Oh, is it just that we're in opposite rooms?
Yeah.
Oh, okay.
Yeah.
So if anybody comes in, I'll just point them across then to you.
Yeah.
I have all my students here, so you shouldn't be disturbed then.
Perfect.
All right, thanks.
Class, guys.
All right. I thought we were in 301. We should have been in 302.
Yeah.
No big deal. Okay. Center of gravity. Did you write that down? Yeah. Continue. I can continue? Yeah. Yep. Okay, so do I have to do that? Okay. The center of gravity. Well, actually, before I give it to you, I wonder if anybody knows it. Do you know center of gravity? Do you know center of gravity?
Yeah.
Possibly, yeah. Go on, give me a sentence. Explain center of gravity in one sentence. Make sure it has a verb. Not quite. What do you...
Like
Yes?
a circle
Yes?
this point.
True. This is true. What about if it's not a circle?
Rectangle?
It's
Okay.
always perpendicular to the ground, right? No? Like straight to the line to the ground?
You're getting a bit better, but not quite there. No, that's too complicated. Keep it simpler than that.
The middle.
This way?
The middle's close.
The center.
The center of gravity is where the center of the gravity is. Okay, I'm not quite hearing what I thought I might hear. The center of gravity of an object is the point at which all the weight acts. So in other words, if you have some object, the point at which the weight force acts to pull the object down, this point here is called the center of gravity. It's the point on the diagram in which the full weight acts. This is the definition of the center of gravity. Now what you were thinking of is the way to find the center of gravity, which you might actually remember from middle school. If you have some object, what you do is you hang this object and then you draw in pencil a straight line down. Then what you do is you turn the object and hang it from a different side and also draw a straight line down. And where those two lines meet, that's the center of gravity. Now, maybe you've done this in class. You remember doing this one? Or you've seen this one? Yeah, so you hang it, you draw a line, and then you hang it from somewhere else and you draw a line, and this is how you can find the center of gravity. Anyway, it's the point through which the full weight of the body appears to act. So definitely write this definition down, since nobody gave it to me as nicely as this. Okay, continue. Yep. Do you need a minute? You're good? Okay. The center of gravity basically is where the weight force vector acts. how the mass is spread out will affect the centre of gravity. So how the mass is distributed will change where the centre of gravity is. So obviously, if you take a table like a rectangle, the centre of gravity is right in the middle. But if, say, this side of the table is heavier than this side, because maybe I have the projector, my coffee and all that, what will happen to the centre of gravity? Will it still be in the middle?
No.
No, it will shift towards this end here. Yeah. Another way to think of centre of gravity is that it's like the average mass point. It's like some kind of average. Precisely is not important right now. Okay, so in these three pictures, who is most likely to fall? A. And what's the reason? Yeah. So we kind of understand that when the centre of gravity is high, it makes it easier for it to fall. This is very important in engineering. Can you think of an example in real life, in engineering, in manufacturing, where this is a really big deal?
Bridges.
Buildings, true. Buildings don't usually fall down. Something else though. Something else. Think transportation.
Bus.
Yes, very good. What about the bus?
Two-story bus.
Yep.
It might fall when it turns the center.
Correct. Yeah, especially if everybody sits upstairs and nobody sits downstairs. Yeah. Because what would happen then? Centre of gravity will be higher then. Yeah. In fact, now I don't know if this has happened to you, but if you take flights in Europe, sometimes what happens is they have to change the plane. So, for example, I think that when I was coming back from Manchester or something, I don't remember, the plane that they got as a replacement was actually bigger than the original plane. It meant that some of the seats would be empty because there was more seats now than passengers. So what they do is they don't let you sit in the first three or the last three rows, because they still want to keep the centre of gravity of the plane in the same place. You see, imagine everybody sat up the front and the seats down the back were empty because people want to be near the door. What would happen to the centre of gravity of the plane? It would move forward. The pilot would actually notice this when flying. So in these situations, they don't let you sit at the top or the bottom. You only have to sit in the middle when this happens. Has that ever happened to anyone on a flight? No, because I have a feeling, because your flights are so long, they're already big planes. Yeah. It's unlikely to be a bigger plane that replaces it. So, there is another important example. In America, the SUVs? You know SUV, this car?
Yeah.
Do you know SUV? It's the like very high, like a Jeep. Yeah. What's an example? Honda maybe? No, Honda's okay. It's the American. It's a Hummer. Yeah. Although Hummer's okay because the base of the Hummer is very heavy, so the centre of gravity is quite low. No, that was it. Yeah. When the Hummer came out, it was very expensive. So some American car companies make cars that look like the Hummer, but were cheaper. So because they were cheaper, they were not as heavy. Because they were not as heavy, the centre of gravity was higher. So when the cars turned the corner on the motorway, fall down. So centre of gravity is quite important for engineering, and we want to keep it low. This is why the F1 car, Formula 1. Yeah, it's very, very low. The driver is like here, near the ground. Okay, so some vocabulary. Does anyone know this word Fulcrum? No? Yes, go on. What's another word for it, maybe? If you can think of another word for it. Huh? Yes, in the lever system. Which part of the lever system? Not quite the centre. I think of another word. It's the point where it turns. Yeah. The hinge, like the hinge, yeah. A fulcrum is another word for a turning point or a pivot. It's the point at which the object turns. For example, on the door here, Where's the fulcrum here on the door? This part here, the hinge. This is the fulcrum, because this is where the door turns. It turns on this point. Okay, so that's the fulcrum. Okay, so you need to write these words down for sure.
Is that why quite different or like?
Yeah, I have a feeling that they get narrow as they move up to try and lower the center of gravity. Yeah, I think so, yeah. Also, the other reason for the narrowing on the top is as you move up, you get more wind. So you, just like in the example I did in the last class, you want to reduce the area so there's less force on the top. Because the force on the top is what could make it sway. Continue? Yep. Okay, for example, the hinge on a door. The center of a seesaw. You know a seesaw? You know a seesaw? You know, the kids. Boy. Seesaw, yes. Of course, everybody knows seesaw. The wheels in contact with the road on a car. This is actually a turning point. And you know it's a turning point because when it turns too fast, it falls over. So it's a turning point. Your foot on the ground when you're walking. These are all turning points. These are all fulcrums. Because, you know, when you put your foot on the ground, you turn on this point. So it's also a fulcrum. Yep. Right. So, notice how the center of gravity is above the turning point. So, is she likely to fall or not? Well, she's a professional, so she won't, but it's quite difficult. There's also a second problem for her that makes it easy for her to fall. What is that? So the center of gravity is quite high for the gymnast, but there's another problem that makes her job more difficult. What's that? Very good. The base is quite small. Now this is even worse for a ballerina. Do you know a ballerina? So how big is the base for a ballerina? It's like this big when they stand on their toe. So is it likely they fall? Very likely. So the base is quite small, her hand, so she could easily topple. We call this system very unstable. It's very unstable for two reasons. The turning point is the center of gravity is above the turning point, and the base is small. Can you make some note of that? Very unstable. Turning point, center of gravity is high, and the base is small. I'm going to the ballet next month. I told my wife I'll take her, so I have to buy tickets. So I thought it would be good to do this type of example then. Have you ever seen pictures of ballerinas' toes? You've seen those pictures? Pretty freaky. Because they're so much force on their toes, it really messes up their toes. So if you want nightmares, just go to Google Image and type in ballerina's toes. Not pleasant. Think about this. My center of gravity, high or low? Wow.
High.
I'm tall enough, so high. My base?
Yeah.
Small enough,
Yeah.
right? So stable, unstable, how would you describe it? No, I'm unstable. We're unstable because my center of gravity is high and my base is small. So why don't I fall? Why is it that if I'm unstable, my center of gravity is high and my base is small and I don't fall? Or that you don't fall? What's the reason?
Yes, strongly.
Why, thank you, but no. What's the reason?
Because you have the ability to maintain your...
Yeah, but why? How can I maintain it? But what's the reason that lets me stand and walk.
Wait.
No.
Yeah, you walk the base to get
I know, my shoes stay the same size now. They don't get any bigger.
the bone
There's
must
It's not
Not
external
quite.
force.
No. This is the reason.
Yeah, you have it here.
Yeah.
Yeah, I know this.
You must understand that your brain is doing a lot of work to keep you balanced. This is why it's so difficult to make robots that walk. Did you ever see videos of robots trying to walk? You know, they're always falling down.
Yeah.
It's quite difficult because they're unstable. Human brain is very powerful at balancing, keeping everything balanced. It's actually quite unstable to walk. This picture here, this is unstable, but it's not very unstable. Why not? The centre of gravity is high, but the base is quite big compared to the size of it, you know? Like this here. Now the base is nearly the same size as the whole object. It's only a little bit bigger on the top. So because the base is quite big, but the centre of gravity is still large, high, we call it just unstable, not very unstable. So it could still fall if I push it, but it won't just fall by itself, it will just sit there. Okay? So the next one, if you can write this down, unstable, bigger base, but centre of gravity is still high. Okay, continue, yeah. The next one is, now, some people know this toy and some people don't. It's the bird that you put on your finger and it balances. Does anybody know this toy? You know this toy. You know this toy. No?
I know.
You know this toy? You know it. You know this toy? Did you have it as a kid? It's the bird, and you put the bird's beak on your finger and you can balance the bird. Now the reason you can do this is because the centre of gravity of the bird is actually at its beak. So it means the turning point and the centre of gravity are the same point. We call this object neutral. So it won't fall, but if I hit it, it will still move. But it won't fall off my finger because its centre of gravity and the turning point are the same point. So it's kind of like this. Here's the centre of gravity, and if I put it on the table, it's nearly at the same place as the turning point, although it's a little bit higher. You know, like here, this is the turning point. The centre of gravity, it's nearly at the turning point. So in these situations, we call it neutral, when the centre of gravity and the turning point are the same. So the centre of gravity is at the turning point, the beak. So even if a little force is applied, it may wiggle or move, but it shouldn't fall off. Yeah. So like here, if I push it, would it fall? No, it'll move, but it doesn't fall. Yeah. So we call this neutral. Neutral, if you want to write that down, please. Neutral. Centre of gravity is at the turning point.
Centre of gravity is
at the turning point, yeah. Now it's not. Yeah. No, the centre of gravity for the bird or for the pen. The pen is in the middle, but we can't quite make it at the turning point. It's like maybe 1 millimeter above it. But for the bird, they designed this bird toy so that the centre of gravity is exactly at the beak, and the reason is because of the wings. The wings are quite heavy. It pulls the centre of gravity towards the beak. Can you see these wings?
In order for it to be the centre of gravity to be here.
Oh, you see, this is the thing. If you wanted the centre of gravity here, you would need something that comes out of the pen that's quite heavy. Actually, do you know what? I'll give you another good example of neutral. This lad. When the people are training to walk across the rope, actually I should really have him holding this. No, wrong colour. When they're walking across, if he doesn't hold this, where's his centre of gravity? His centre of gravity will be about here. But in this picture, because these weights actually, if you were to look at it straight on, these weights actually hang under the rope. So it means the centre of gravity, what happens? It moves down. And you can pick the weight so that you can get your centre of gravity right here at the turning point on the rope. This means he is neutral, meaning that it's easier for him to walk across the rope. So when they're first learning how to do this, they practice using these weights to make the centre of gravity at the turning point, so it's neutral. Yeah? You've seen this before, haven't you? I mean, this, you know what I'm talking about here, yeah? Okay, continue. So next one is stable. In this picture, the centre of gravity is below the turning point. So actually, it's like hanging. If I hit this, it doesn't matter. It'll just swing and not fall. Although, he's not very stable because the base is quite small, so it could still fall off. But we say it's stable because the centre of gravity is below the turning point. We call this stable.
Why don't you call the neutral?
Yeah, it's like it's on the point of being in between the two. So if I make the centre of gravity a little bit higher, then it will be unstable because it could fall. If I make it a little bit lower, it will be stable. So it's because it's on the point of going either way, we call it neutral. In this one, it's below, yeah. Okay, so can you write that down? Stable centre of gravity is below. You don't look happy with this. What's the problem? Well, where's the turning point in this picture? His hands, yeah. Yeah, because this is where it's turning. But where's the centre of gravity? Is it above his hands or below his hands? Below. So we say it's stable in this picture. Okay, next picture. Very stable, because the centre of gravity is below the turning point and the base is very large. Will this ever fall? No, I don't expect this door to ever fall. Yep. Continue? Yeah. So, let's see. So we've talked a lot about, things turning, but we actually haven't said how you measure how easy or hard it is to turn something. So we have this thing called the moment of a force. And it's the force times the perpendicular distance from the fulcrum. Let me just draw that. Let's imagine I have this here. This is the fulcrum. And this is the distance here. And I have somebody, and they're trying to turn this. So they're pushing this up with a force F to try and make this turn. How do we measure this turning force? Well, we don't actually care about the F, and we don't care about the D by itself. it's the two together that's important, because you understand maybe that if the F is small but the D is very big, it's easy to turn. If the D is very small, then we need the F to be bigger to make it turn. Like if we think about the door, which is easier for me to turn the door? If I pull here or if I pull in the middle? No, here it's a bit easier. Here rather than here. Now if I want to open this door, the hardest way I could do it is if I try and grab something here. Yeah, you can imagine I really need a lot of force now to turn the door. And if I try to grab the hinge, could I open the door? No, I must have some distance from the turning point. So it's not only the force that's important, but also the distance. So in this picture here, you care about the two together. So the what we call the turning force, another word for it is moment or torque, is simply this formula. The force multiplied the distance. Now I use the letter L, but I sometimes use a different letter for turning force. I'm going to try and use L more. So what's the unit for turning force? It's Newton meters. Although sometimes I use these, well I should never use J actually. Sometimes I use these letters for turning force. I'll try my best to use L. Huh? No, I shouldn't use J because J is actually something different. Does anyone know what the second letter is there?
What?
Yeah, but what letter is it? It's not quite a T. It's a Greek letter. Does anyone know their Greek letters? Yeah, they're the ones at the start. What about towards the end? Tau. Tau. And what's that third letter? Also a Greek letter. Not upside down L, no. It's a Greek letter. What is it?
It's also a Korean.
Is it?
Is it?
No, it's not.
No.
It's like the doesn't.
No. It's a Greek letter. Does anyone know it? No, I think you do. It's gamma. Capital gamma.
Karma.
Yeah, you are probably thinking of small, lowercase gamma. You know your Greek letters. Alpha, beta, gamma.
Gamma.
Alpha, beta, gamma.
Oh my god.
Delta, delta. Yeah?
Sigma.
Sigma, sigma. Pi, pi. Yeah? Tau. Just like English. Funny. Yeah. Okay. Now, just to be clear, in this formula, I just want to explain exactly what the F and the D is. So you can write this in a moment, but if you just look at the picture here, it's the perpendicular force that you care about. It must be perpendicular. It must be. If it's not perpendicular, you have a choice. Let me draw a picture. Here's the picture here. This is D, and let's say this is F like this. Okay? Perpendicular distance or perpendicular force. They have to be perpendicular. What you could do if you had this situation is you could resolve this into Fx and Fy. And which one would you use? You'd use Fy. So you'd say D multiply Fy. Or there's actually something else you could do. I wonder if anyone knows what else you could have done. Now usually this is what you should do, but there's actually another way you could fix this. Does anyone know? If you can actually still use this F, but you shouldn't use the D. You should use something else instead of the D. You can use this distance. To make it perpendicular. Now, that's kind of messy to do, but it could be done. But really, 99% of the time, the easiest thing to do is this, where you take the F and you resolve it into a X and a Y, and you reject the X and just use the Y. You don't care about the X because when you're trying to turn a door, if I'm pushing this way at an angle, the force that goes into this hinge does nothing. It's only the force that's perpendicular that does anything, okay? So, you can think about the formula like this as well, if you want. Okay. I don't know what you need to write down. I don't know if you want to draw the picture or write this down or what. Now, please note these other words. These all mean turning force, moment, torque. They all mean the same thing. Okay, I'm going to continue now. Yeah, but I mean, I'm going to upload it too, so you can get it from the YouTube video. But you take a picture. Okay, continuing now. So you can see in this little picture here, you can move something quite heavy. Even if you have a small force, you can just make the distance very large. A very particular turning force problem is something called a couple. This is actually quite special because in these problems the forces are always equal and opposite, and we have these situations when we want to turn like a wheel. Think about this. If this force was bigger than this force, it would mean the steering wheel moves up. Now when you drive your car, this does not usually happen. The steering wheel stays in one place. So it means that when you push up with this hand and down with this hand, the forces must be equal. The same when you're cycling as well. This force must equal this force. This is a very important system. It's called a couple, the name of this system. It's a special type of system. The two forces are equal and opposite. Let's calculate what the turning force is for this system. Okay? So this is called a couple. So I'll just draw it again here. Here's an example. We have a wheel, and we'll call this distance here to here D, and we'll call this distance, this force here F, and this force here F, and here is the turning point. How big is this distance? D over 2, and this one? D over 2. So what is the turning force provided by, we'll call this 1 and we'll call this 2. What's the turning force from the first one? What would that equal? F multiplied over 2. Now, this force here, what's the turning force provided by that one? The same. So what's the total turning force? You add these together, and what do you get? FD. So for a couple, the turning force in total is just the F multiplied by the diameter. You know this word, diameter? That's the answer then. Okay, so can you note this formula, please? This is for a couple. Yeah, it's the easiest example is like with a wheel. You have equal and opposite forces at the end of something which is rotating, and the turning point is in the middle. Just like a bicycle wheel or something like this, or a steering wheel. Okay, continue. So So a couple is two equal but opposite forces that are a distance d apart and cause the object to rotate but not move linearly. The total turning force is Fd, which we just proved. You don't need to write that definition down. If you have the picture and the formula, that's really enough. Okay. Now, we've got a couple of questions. A man is trying to free a car that's trapped under some mud. He uses a 2.2 meter steel pole. He puts the steel pole under the car's wheel and then uses a large brick as a pivot. The brick is 20 centimeters from the pole and the man pushes down to try and lift the car up. What is the moment? So, it's force times distance. What's the force here? What did I say the force is? How hard is he pushing down? 1 kilonewton. And what's the distance to the turning point? 2 meters. Yeah, very good. Because I said it's 2.2 meters long, but I said the pivot is 20 centimeters from the end. So this is the turning point, and the man is pushing down here to try and lift the car up. So it'll be 1,000 times 2, which is 2,000 Newton meters. Okay, that's okay. Right, now here's one for you to try. A wrench is used to tighten a nut. The wrench is 20 centimeters long and you're using a force of 100 newtons. What is the moment? Yeah, what is it? 20 what? Newton meters. Yeah. Now, I said the true value is not really this, though. Why not? Well, it's not really this because here's the wrench, and I have to turn it. I do not hold the wrench at the end like this. I grip it like this, which means it's not really 20 centimeters. Maybe it's only like 15 centimeters. Because I'm not turning it like this. I'm holding it from the end. So it's less than 20 Newton meters. A woman turns a steering wheel by applying a force of 5 newtons with her left hand and 5 newtons with her right hand. The steering wheel is 30 centimeters in diameter. What is the couple? Well, what is the total turning force here? What would it be? 1.5. 5 multiplied 0.3, which is 1.5, and the unit? Newton meters. So these are all quick, short questions, nothing too difficult here. These will not take you much time to do. So if you can try and do this as well. When's our next physics class? Is it tomorrow? Must be tomorrow.
Yeah.
Tomorrow.
Everything's
back to normal. Only today had the extra class. I will take you for assessment support on your timetable as well. What room are we in tomorrow? At what time?
9.
Double class?
Yeah.
And do we have a class after lunch?
No?
No? And on Friday? Double class? Oh, we have a single class at lunchtime about.
Yeah.
And then we have a class at 4?
Yeah, 4 and 5.
Okay. Yeah, I know, you don't like it, I don't like it, but you know, that's what the principal scheduled, so that's what we have to live with.
After the break and
Look, you only have to do this for 1 year. I've been doing this for 10 years, okay, so you don't have much sympathy from me. Alright, we'll finish there, so